Hello, my name is Ashish Deshpande. I'm an associate professor of mechanical engineering at UT Austin here in the US. I'm also co-founder of Harmonic Bionics. It's a huge honor and distinct pleasure to be presenting my research in front of you as part of IROS 2020. I would like to thank the organizers, especially Dr. Paul O for inviting me, and huge thanks to you for listening to me today. Today, I plan to share with you parts of my journey along an exciting and challenging path towards building robots for rehabilitation after stroke. I'll show you the robot that my group has designed and built. I'll present results, both technical and human testing results. And I will also tell you about my experiences in commercializing this technology through my startup. Let's start with the definition of the problem. Stroke is a leading cause of disability in the US, and more than 800,000 strokes happen per year in the US alone, leaving millions of people with disabilities. Fortunately, more and more people are surviving after stroke, but with number of instances growing and more people surviving, the number of stroke survivors is growing and is projected to grow in the coming years, as shown in this plot. This has resulted in severe cost at all levels: personal, family, societal, workplace, and economical. I am motivated to build robotic tools that could help alleviate this huge societal problem. Let me start out by showing one of the robots that my group has built, the Harmony exoskeleton. In the coming video, you will see a model in our latest version of Harmony. You will see a variety of upper body movements. At times, the model is moving and Harmony tracks, and at other times, Harmony moves her. Hope you like that. Now getting back to the problem itself. Let's meet Mr. Avril Seal, who is a colleague of mine here at UT Austin. He suffered a stroke 2 years ago that left him partially paralyzed on the right side of his body. After many weeks of treatment, both in the hospital and outside, he was able to walk again. But he was left with limited use of his arm and hand. He's relatively young, healthy, and very motivated. So why did the best possible treatment not lead to full recovery for him? Could robots help with the therapy that results in better and faster recovery? We'll come back to Avril's story in later parts of this talk. Let me give you some background on stroke. Stroke happens when a blood vessel carrying oxygen or nutrients to the brain either is blocked or burst. Acute treatments have improved, resulting in more patients surviving after stroke, which is great. Still, stroke results in deaths of cell in the brain, and that results in disability. While stroke can present movement, speech, and cognitive disabilities, focus of my work is on movement recovery after stroke. More specifically, recovery of arm and hand function. This is especially critical because more than 80% of stroke patients have arm and hand disabilities. And unfortunately, less than 20% recover fully, just as you saw in the case of Avril. Post-stroke rehabilitation, which consists of physical and occupational therapy, aims to overcome the movement disabilities caused by stroke. So how does the rehab work after stroke? Let's take Avral's case. He was in inpatient rehab for 10 weeks, during which time he received 3 hours of therapy per day, and one of those hours was dedicated to upper body. Therapists worked on a number of issues with him, starting with weakness, tone, and spasticity. Then I also started to get him to move, where weakness, lack of coordination, shoulder subluxation, and certain synergies that were unwanted played a big role. Fortunately for Avral, rehab started right away, and he received really good therapy. But still, recovery is limited, especially in the upper body. Could he have benefited from greater intensity and higher dosage? Could this therapy have gone much longer than what he got just for a few weeks? Averill definitely thinks so. But currently, that's not possible because of cost, labor, and resource limitations in current therapy. Another key issue is what happens during therapy. With limited resources, the therapists focus on functional recovery so that they can send people back home to living their lives. This is a laudable goal, and in itself, it's not easy. I've seen it firsthand. My sister is a stroke therapist, and the dedication and hard work is laudable for my sister. But the focus on getting daily functions back could teach patients to compensate, and this could get in the way of true recovery. Typically, at first, primitive behaviors come back. So in case of arm, there's a flexion synergy that starts to come back as they learn to move. With limited time in therapy, the patient may be left with compensation using these maladaptive behaviors such as the flexion synergy. Is there a way to target true recovery? This would require substantial change in the patient's neuromuscular system. And this is a very difficult task, way more difficult than, say, to train somebody like me how to shoot basketball. Just repetitions won't do, even with high dosage. So the big question is, how can we nudge the brain and the body system of these stroke patients toward true recovery? This is the fascinating and challenging question that drives my research. To alleviate the challenges of stroke therapy, a number of robots have been developed over the last few decades. These are fantastic machines designed by the leading research groups around the world. Some of these robots have been tested on stroke patients, and the studies show that recovery after robotic therapy is comparable to recovery after high dosage of conventional therapy. On one hand, this is a bit disappointing because we anticipated faster and better recovery with the robots. But on the other hand, this is promising because studies show that the robots are safe and effective in delivering complex therapeutic interventions. The robots took physical labor away from the therapists, and the robots helped in increase of the dosage. It's possible that the limited success might have been because the robotic training may not have targeted the true recovery. First, some of the robots targeted limited motions, for example, just the planar motion. Even with advanced control, the patients were moved passively, thus limiting the effect on the neuromuscular system. Most of the robotic training is implemented in the chronic stage, that is, many months after stroke. But the research shows that right after stroke is the best time to be able to affect the brain-body system, especially for true recovery. So, as a summary, what's missing in the current stroke therapy and current robot devices? What is needed to cause true recovery? First, we must be able to systematically target resting state abnormalities by stretching, assisting while maintaining healthy biomechanical coordination. We must be able to target voluntary movement disabilities by overcoming lack of coordination and training against synergies. And we must be able to do this really in the early stage and all the way through the recovery process. We must be able to do this at high intensity and high dosage. And we must have a way to monitor progress during this whole process through rapid assessment. Inspired by the need in stroke rehab, promising success of other robots, and also by the open scientific and technological challenges, my group embarked upon the development of Harmony. In Harmony, we have achieved a robotic system which we believe has many of the desired features I listed earlier. We believe that Harmony has a potential to serve as a tool not only for stroke treatment, but also for scientific discovery and assessment. In the upcoming slides, I will show you some of the key features of Harmony: the shoulder mechanism, torque control feature, bilateral feature, and also suite of sensors. Let's talk about some of the methodology through which we achieve all the features of harmony. Let me talk about the shoulder joint, which is one of the most complex joints in the human body. The shoulder is often modeled as a ball and socket joint, but there is more going on here. There is scapula joint that's floating in the back of the shoulder. And in healthy individual, it moves in coordination with the ball socket joint in what is called a scapulohumeral rhythm. This is particularly important in case of stroke survivors because they often exhibit shoulder impairment either through a separation of the arm from the shoulder or through impaired coordination. And proper assistance must be provided to this population to avoid creating or aggravating shoulder injuries. Towards this goal, we model the human shoulder as a 5 degree of freedom system. 3 degrees of freedom to represent the ball and socket joint, and additional 2 degrees of freedom for elevation and depression, and protraction and retraction of the shoulder. We came up with a kinematic solution that has 5 degrees of freedom, that supports 5 degrees of freedom of the shoulder. That includes a parallelogram system on the back of the shoulder. These pictures show the basic kinematics that drives harmony's shoulder joints. That gives us 5 degrees of freedom at the shoulder, and 1 degree of freedom at elbow, and 1 degree of freedom for wrist, pronation, and supination. That gives us total 40 degrees of freedom on this two-sided robot. We came up with our own solution for actuation, and we had to find a way to arrange the actuators and linkages so that they don't bump into each other, neither does the robot interfere with user's motion. Here is the final design of the whole system. To show our shoulder actuation system in action, I'm going to show you a video in which my student, Anna, is going to carry out a number of arm elevations in harmony. I want you to look at the joints aligned with her scapula, which move together to track her motion. We carried out testing with healthy subjects, and we confirmed that large workspace and healthy shoulder coordination were achieved. The gray dots indicate locations of the participant's wrist, and the orange dot indicate locations of the shoulder joint, confirming coordination was maintained throughout the range of motion. Let me dig a bit deeper into the actuator design. At each joint, we included a series elastic actuator, which allows us to achieve closed loop torque control at high loop rate. The torque control allows us to implement a variety of control strategies, such as force and impedance control. This is particularly important during rehab, where our goal is to substantially affect patient's brain-body system. Toward this goal, we are able to implement a variety of control modes, such as gravity support, assistance, resistance, correction, and even unstable mode to encourage arm control. Baseline control of harmony includes a feed-forward term that captures the inverse dynamics to enhance transparency and also to provide support for patient's arm weight, and a feedback term that tracks shoulder motions while maintaining correct coordination. Additional control terms could be added to meet the variety of neuro rehab goals. We carried out a multitude of tests to examine the control performance of harmony. And here I'm going to show you a few results. We tested the robot's force tracking performance in the Cartesian space. In this test, we provided force step input in force in Cartesian space and tracked the force at the end in the end effector. The x-axis in all three graphs show time, and the y-axis show forces in three directions, x, y, z. The results show that accurate tracking was achieved in terms of force tracking. We also tested force tracking in sinusoidal references and found similarly good performance. Again, x-axis is time and y-axis is forces in x, y, z direction. We also tested robots' performance during position tracking with impedance control under disturbance. In this test, we provided a sinusoidal reference in z and constant reference in x and y. The arrows indicate the times when we introduce disturbance. Note that tracking performance is satisfactory even under these disturbances. And the robot gently comes back to the reference trajectory and recovers elegantly from the disturbances. In this video, we show that the behavior of the robot during trajectory tracking can be modulated by adjusting the impedance control gains. You can see the contrast between the two sides in this case, where the left side emulates a spring with low stiffness that is gentle to touch, and the right side emulates a position controller with good accuracy but rigid interaction. In rehab applications, we may sometimes want to ensure gentle and soft interactions, while other times we might want to implement rigid interaction while always maintaining safety for the patient. As you can see, Harmony is a two-sided robot. This allows for a variety of cool bimanual applications towards stroke therapy. For instance, we can use kinematics from the healthy side as a reference for the affected side to either mirror the motions or to do more complex bimanual task control. This video shows the mirror mode training. In this video, the left side is relaxed and the right side is controlling its motion. This will become apparent when the left side is detached from the robot. Furthermore, we can support other bimanual tasks as illustrated in this video, where my student Anna is in the transparent mode and accomplishing bimanual tasks. Harmony has more than 70 sensors that record data at 2 kHz, which makes it a powerful tool to measure many aspects of movements, including kinematics and effort. All right, I will show you a number of features of Harmony. So as a summary, what have we accomplished? We believe that now we have a robot with features that are suitable to target true recovery of stroke patients. We have carried out testing with healthy and stroke participants. Let me show you some results. Results from tests with healthy participants confirm the safety of the robot and also controller performance. We also carried out preliminary testing with stroke patients. We had 5 male participants, all in chronic stages of recovery. They had moderate to severe upper body impairments. Avril, in fact, was one of the participants. We collaborated with clinicians from the St. David's Healthcare here in Austin. Our collaborators included Dr. Robert Lee, pictured here, and therapist Bob Whitford. During training, there were 3 exercises that focused on arm extension and shoulder coordination. We wanted to focus on passive stretching and working against flexion synergy. Our controller encouraged the patients to initiate the motion and only assisted when needed. The dosage was 1 hour a day, 2 days a week, and we had a total of 7 sessions per patient. In all, each subject completed more than 1,100 repetitions in the robot. Let me show you a video of Avril getting training with the robot. So what were the results? Overall, we received enthusiastic response from everybody. There was no pain or adverse events. We found high levels of safety perception and low anxiety levels. The time taken for getting in and out of the robot was also short, which is critical in clinical applications. Healthy shoulder coordination was achieved even for those patients whose shoulder was subluxed. Notice the shoulder put in place in Harmony. See the right picture here, which typically pops out. See the 2 black lines on the left picture. It was true for all patients. This is very important for clinicians, and this confirms Harmony's design and control are satisfactory. To assess the improvement quantitatively, 2 standard and commonly used tests were administered by the therapist. During these tests, the therapist asked the patients to finish an action, observes, and assign scores. The Fugl-Meyer test assesses impairment, so it involves free motions, and the ARAT test assesses functional recovery, so that involves manipulation of set of objects. The assessment is administered pre and post robotic training. Did the scores improve? Yes, the scores did improve on both scales. The table show pre and post scores for the two tests, and the plot show pre and post scores, both individual and average. The scores, however, did not cross the threshold of minimal clinically important difference. In addition to this training, in the last session, we let all the participants try out our mirror mode. As a reminder, in this mode, the healthy side of the patient drives the affected side through coordinated control. Take a moment to watch joy on Averell's face as he gets to control his affected side for the first time in a long time. He loved the fact that he was in control of his affected side. He also loved the fact that he was able to give himself what he called delicious stretches that he's not able to do. As I said, this was quite revealing, and we're going to study this deeply during our ongoing studies. So what's next? As a summary, I have shown to you that we have successfully built a robot that has a number of advanced features. Testing with healthy folks showed that robot is safe and effective. Early testing with stroke patients showed improvement. And we are optimistic but cautious because we only tested with 5 patients and the improvements have been moderate. Our training was short and it was delivered in the chronic stage. And we primarily moved the patient in a passive manner. So although our robot has a number of suitable features to tackle true recovery, we haven't fully exploited these. So the improvement might have been because of distal or biomechanical changes. That is strength improvement, spasticity improvement, or some learning on fixed neuromuscular system. The question is, can we affect the neuromuscular system substantially? Can we nudge it towards true recovery? This is what we're exploring with our ongoing research. I'm collaborating with top clinicians around the US to implement early stage testing with Harmony. For example, a combination of corrective and resistive training, natural movement in full ranges of motion, and therapy that's engaging in challenging and given in high dosage and intensity. I'm also collaborating with top neuroscientists, including Dr. John Krakauer from Johns Hopkins University, to target impairment with combination of biology and technology. To examine if Harmony can affect motor learning both for healthy and stroke patients, I'm collaborating with Dr. Peter Stone here in the computer science department. I'm exploring if we can use Harmony as an assessment tool. With the rapid and accurate measurement of kinematics as well as effort, I believe that we can understand impairment much better and quantify recovery much better with Harmony. Toward the goal of improving neuro recovery, we believe that the robot must be brought out of the lab to the patients and therapists and clinicians and scientists. With this in mind, we've launched Harmonic Bionics. This was initiated by my former student, Dr. Youngmark Yun, and soon we were joined by my another former student, Rohit, and an experienced business leader, Chris Prentice. In fact, there's a fantastic tradition of Renew Robotics lab members founding and playing a key role in early stage startups. These folks are making amazing contributions in the growing robotics startup culture here in Austin. I'm really proud of them. At Harmonic Bionics, we have designed and built a product version of Harmony. It's the robot I showed you earlier. We're also engaging with hundreds of customers, therapists, hospital administrators, doctors, and receiving really good response. We are on our way to bring Harmony out of the lab towards the goal of treatment, science, and assessment. In the big picture, I'm motivated to combine the cutting-edge knowledge from biology and my expertise in technology to improve stroke rehab. Beyond stroke therapy, Harmony has the potential to help with training, for example, of astronauts, athletes, and soldiers, also with assistance to, say, spinal cord injury patients, soldiers, and factory workers, and also in entertainment, for example, with gaming system that provides full body haptic feedback. None of this work would be possible without the fantastic effort by the members of Renew Robotics Lab. A big thanks to my amazing group. I would also like to acknowledge my clinical and research collaborators and also all the contributors to the Harmony project over the years. And finally, I would also like to thank the funding agencies and study participants, including Averell, who continues to be a source of inspiration for us. Let me take a moment to plug Averell's upcoming book about his experiences with stroke and rehab. Let me also acknowledge the fantastic collaborations afforded to me by the Texas Robotics Group. We have brought together top-notch researchers under this umbrella organization, and we are pushing towards two big research themes: general purpose autonomy and human-robot interactions. In closing, thank you very much for your attention today. I really hope that I get to meet many of you in person sometime real soon. Thank you.